Alright, hell yeah. So this problem was sent in by a German student, and I just want to throw out the word like, hey, send me links to problems, you know what I mean? Just write them in the description. Sometimes they're already on, I can search for them fairly easily. But yeah, just anything that motivates me is always the best problem to do when you're just kind of like, excited about it. But this one was cool. The student had the professor showed a unique method of solving that was pretty cool, and we can get to the fundamentals. And I'm still new to this, but we're going to talk about some things about like why you can do things. Okay, so hell yeah. So we have a force coming in, and then we have a tripod. These are rigid structures, but they're all pivoted, and so they only have a force along the legs, and so they can either be in compression, or when you pull on it, this one's probably going to be in tension. So you can kind of see that this leg's for sure going to be in tension. These might be in compression. This might be in tension though, and there's this idea in statics that this force has, like, we have an x component and it's a downward in the y component. So if I'm coming here, this is my downward in the y, and you do the parallelogram method. So if I'm going here to there, how do I get there? I can go this direction, and this direction. So that's going to be down in the y. Oh, no, this is my y-axis. So this is going to be down in the z, negative in the y, and then over or negative in the x. And the parallelogram method says you can get there three different ways. So if I'm going up this height, I'm just going to measure that height over here. And if I'm going this distance over, so you just box it in. And to get to here, I can go over this direction, and this direction. Cool. And I guess if it's in 3D, I can go the parallelogram method. You can go a bunch of different ways. I can go this way in the y, this way in the x, and then this way, y, z, x. I could go x, y, z. Yep. So one way, two ways, three ways, four ways. I could go this, 5, 6. I don't know. So maybe there's up to 6 different paths that I could take. Anyway, and then so what I can also say is that this force can be represented as 3 forces. It could be just this force in the x, go in that direction. It could be this force in the z. So we have F of x, F of z, and then in the y we have F of y. And then what we do is that, hey, we have a point here, and we can say that what I like to do is say, hey, that's just a chunk of mass. And from a Newtonian perspective, if I put a force this way, what I'm going to see is F equals ma. And this is kind of the free body diagram. I'm going to chop this little chunk of mass out, and then what I do is pretend like it's the only thing in the universe, and then go back to the problem and say, well, we have a known force on it, and maybe that force is just in this f of x direction. And if that's the case, it's going to be moving in that direction. It's going to change its velocity. If its initial velocity is 0, we're going to get an acceleration because we have a force in that direction. But this is a branch of physics called statics, where we know by observation that little chunk of mass ain't moving. And so there must be a force this direction that's equal to f of x, due to S1, S2, and S3, all those that have to be balanced. And these forces also have components. They have, we have a negative. If I'm going to S1, I'm going to go down a z. I'm going to go over an x in the negative direction and negative y. So I'm going to go negative z, negative x, negative y. And that component, and so, so I went this direction. So this direction in the S1 is going to be kind of the vector of S1. That's going to be S1 of x. Okay, so yeah, so we have this idea that this force, f of x, is going to be balanced by s1 of x plus s2 of x plus s3 of x. Now these can be positive or negative, but those are going to equal this force being pushed on it. So then the aha moment was like, alright, hell yeah. So now what we get into, this video is like, hey, if I have a vector, so if I have this f, and it has 3 components, so f is a vector, and it's going to have an f of x in the I hat direction, plus f of y in the j hat direction, plus f of z in the k hat direction. And even today, I had no idea what the hell, the hat on top of an I, j, and k actually meant. I missed the day that they were talking about unit vectors, and unit vectors are kind of confusing anyway. But directionally it's just, hey, this I hat is synonymous with this x direction, j hat is synonymous with the y direction, and k hat is synonymous with the z direction. But these themselves are vectors, and they're 1 unit long. So we have a vector in the x direction, and it has a length of 1, and so it's 1I. That is the definition of, well, I guess I shouldn't have said 1I hat. It has a length of 1, and it is in this x direction. How do you say this? Yeah, and then so it that represents oh yeah, it's tripping me out. It's hard to say this any other way besides using the I hat, j hat, k hat terms. But if I had a vector with a magnitude of 1 and it was in the direction of x, how would I represent that? Let's say I just come here and say that's going to be I hat. So the definition of I hat is a vector that has a magnitude of 1, just like this is a vector that we have components. It has a component in the I, j, and k directions. But now a vector has a magnitude and a direction. So what direction is this in? Well, I could just say 1, in the x direction. And so it has a magnitude and direction. So that's the vector I hat. And maybe I don't know if I'm satisfied that they used I, j, and k, because it seems like you could also have just done like x hat, because that's the direction, and that's a unit vector in the x direction. Like if here's my x, y, and this is 1, 2, 3, this is my origin, this is A, this vector is OA, it is a magnitude of 3, and it's in the x direction. Why couldn't I have just done x hat? But definition, you could do this, but definitionally, what is x hat? Because this gets into the idea of what I'm talking about, is if you have a vector, what can you do with it? Can you multiply? In this case, we're taking, this 3 is just a scalar, and then this is the vector. But this is the vector with a magnitude of 1. So if I draw my picture again, x, y, and I do 1, 2, 3, this vector that only goes to this distance, that vector is, and then let's just say it's OA, or OA prime. And we're going to say that has magnitude of 1, and it's going to be x, x hat. So it's in the direction of x, and it's a magnitude of 1. Oh man, I have a struggle with defining things, but yeah, so this x hat is this vector right here, and this vector, we can just multiply it by 3, and hell yeah, you'll get up to here. You know what I mean? So just multiplying a vector by a scalar just increases the magnitude of that vector, does not change its direction. Okay, so we have this vector f, and what we're going to do is take that vector f and then dot it with a unit vector in the I hat direction. So we're actually just going to dot it with I hat. And so this vector f might have a magnitude of like 20. I don't know, doesn't really matter. And just in general, if this is 20, it's the hypotenuse, it's the largest number. And then we shadow it down here, so we say like, hey, and then the geometry way to do this is like divvy it up into halves, or in this case, we'll divvy this up into thirds. So if and we're going to say this force is 100 whatevers, you know, newtons or whatever. So if this force has a magnitude of 100, and then that's the way you would represent the force is a vector, but if we do absolute value, that represents the magnitude, just magnitude, not the direction. And if I divvy this up into thirds, I could say that, hey, this is about, 33, and this, is almost the same distance as that, so we're going to say 95. Okay, so now I know these two components, and now this is a new hypotenuse, and this is a 45-degree triangle, and so now I just know by 45 this is going to be about 70%. 70% of 100 is 70, so maybe this is like 60, 65 at the minimum. So cool. So now I know the component in the f of x direction is going to be between 65 and 70. And that's its component. Now if we use this dot product, the dot product always generates a scalar. You're taking a vector with a specific direction and then dotting it with another vector, in this case in this direction, and then you're going to get a scalar. Well, if this vector is going that way and then this vector is going that way, when you dot it, you're going to get a negative. So that's one aspect of the dot product, whether you get it negative or positive. But you're just going to get, in this case, just a negative number. And then so it feels like you don't have anything because you just took a vector, dotted it with another vector, and you get a scalar. So what does that scalar even mean? But because we're doing a dot product, well, even if this wasn't a unit vector, if I'm taking this force and then dotting it with any vector in, let's say, this x direction, when I do a dot product, I am multiplying this 100 by whatever the vector was in this. It could be 200. So literally, I'm multiplying 100 with 200, and I'm getting, what is that, 20,000? So yeah, so the dot product is still a multiplication. And even though it's a scalar, it represents, it represents, well, I mean, it could represent a distance in that direction. And so that itself would be a distance, and if it's in that direction, you could generate a vector from that scalar. And so I think that aspect is what we do when we dot product, especially when we take a dot product to a unit vector. So when I have this vector f, and I dot it with a unit vector in the x direction, the definition of a dot product is kind of the shadow of this vector. And so if I so from this axis to f, this is the shortest distance right there, and then you would have a plane along that distance. And so if I shine a light directed along this line, let's say, like a plank, it's going to have a shadow that hits the x-axis from there to there. And that distance is going to be that scalar. That's going to give us the number. So when we dot f with in this x direction, that's the number we're going to get. But that number also is in that direction. That's specifically in that direction. So we also know this scalar is the component of f in that direction. So I find that to be interesting, that a dot product generates a scalar, but you know what component of that force in what direction. The direction you're dotting it. I mean, I could take the dot product in any sort of random direction. I could say I have a vector that's in that direction, and it's a unit vector, and then I'm going to dot f with that. Cool. So same principle. I'm going to see that I'm going to take from this point, I'm going to just hit the shortest distance to this line, and that's going to be perpendicular. And then this is a planar surface. And then along this, you know, if I follow along like a stringed line and then set up a flashlight, then this is the shadow that it's going to generate. And that's going to be the component of the force in that direction. Alright, I think I know where I want to go with this. So then I can also take vector S1, S2, and S3 and also find the perpendicular distance to the x-axis. It's perpendicular. This is a plane. Same thing as taking a string along this plane, shining a light, and that's going to be the shadow that appears. So that is the x component, the I hat component of S1. And then so we can do that with all three of these, and we can see that S3 has a component along there, and then this has no component. Okay, so now there you go. So this problem can be reduced to maybe get some extra paper. So this problem can be reduced if I'm just looking down along the x-axis. So now I have the x-axis. I have this force, and I'm going to say this is the midpoint. I have I basically have force. This is the, and then the scalar component is just the f of x component, but I can still say it's in the I hat direction. So even though it's a scalar, you can still treat it like a vector. Then I have this S1, and I'm just going to assume everything's in tension. Well, am I assuming this force is... Yeah, so the force is going to be in this negative direction, but I'm going to assume all of these are in tension, so I'm going to have a vector that way, and then this one is going to be a vector that way. So I have S1 is going to be a short little vector that way, and then S3, so we got S1 and then S3. So this can be reduced to f of x is equal to, so this force has to be equal to these other two forces. So, and I would say negative f of x is equal to negative S1 plus S2. Or if you just wanted to say the sum of the forces equal to 0, I would say I would have negative S1 plus S3, sorry, this is S3, and then minus fx. This is equal to 0. And let's go back to how we did this. How we did this is we took, these are all vectors. They have an I, j, and k component. But what I did is I dotted, which is still multiplying. I multiplied all these vectors by a vector in the x direction. So the solution that really gets you to the answer of this, and I'm probably not going to go over it in this video, is like, hey, if I have this system of vectors, I have f and it looks like this. S1, S2, and S3 also look like this. They would look like S1 would look like S1 of x in the I hat plus S1 of x in the j hat plus S1 of x in the k hat. And again, if I dotted S1 with the I hat direction, I would get just S1 in the x. I would get that value. It's a scalar, but I know it's in the I hat direction. So I can say that this is synonymous with the x1 of x in the I hat direction. So it can be represented as its own vector. And that's what got me confused, because in the solution to this one where you actually simplify things, you take the system of equations and then you multiply, you dot, so yeah, so let's say I have vector S1 plus vector S2 plus vector S3, and then what would they say? You would say, you would say the sum of the forces plus F is going to be equal to 0. So there you go. So we know what F is, and we're just assuming all these are in tension or whatever. But yeah, so we have a system of equations equal to 0. And so the problem says, for one of the solutions, after you do a cross product, whatever, then you can come through and then you can dot, let's say we just have a vector, what should we call it? vector q. So I'm going to dot vector q on both sides. So 0.q, this just becomes 0 over here. And then over here, I would just get a huge scalar, but for the solution, oh yeah, this was the trick, because this q also had, it was also qxi plus qy j hat plus qz k hat. For one, it wasn't a unit vector, and two, it wasn't in one of these directions. So because of that, yeah, so now I know how to kind of end this video. Alright, so here I took f and dotted it with I. Let's say I took f and dotted it with 2i. And then I took S1 and took S1 and dotted it with 2i. And then did the same, S2 and S3, and dotted it with 2i. Well, I'm going to take this 100, multiply it by 2, 200, and then it's going to be the percentage, or the shadow component in the x direction. But this gets back, I don't know if I said it in this video, so I'll say it again. Just fundamentals. Like if I have a triangle, a 2, 1, square root 5 triangle, like what can I do to this? This is what I can't do. I can't take every side and then add 2. Can't do it. Well, you can, but you'll just get a misshapen triangle that won't be a right triangle no more. But what you can do is take a 2, 1, square root 5 triangle, and you can multiply everything by 2. Because that's exactly what we're doing in this example. If I do this, I will get the same looking triangle. It'll just be bigger. So if... And sorry, I don't mind just everything being scratchy, because it's more just talking through the concepts, and I'm just working on talking through the concepts so I can be better for other videos. But honestly, the videos where I struggle are probably going to be way better than the videos where I just hammer home the answer, because that was the big issue with lecturers. The lecturers who could say a correct statement, and knowing that they said a correct statement, they could just move on to the next statement. But that is... horrible for learning. I need the statement to be made, maybe say it in a funky way that confuses, you know what I mean, and then like dial in on what the fundamental of that statement actually is. Okay, so we just showed that we could take this unit vector, we take f and then dot it with not a unit vector, but 2 times a vector in the I direction. And then so everything gets scaled up. So now if... Sweet, I know where to go with this. So if this was my result, so now this is my x direction, but now my f is twice as big. So this is my f of x. And then my S1 is twice as big this way. And then this S3 is twice as big that way. So this is S3. From there, this is my origin. This is S1, and this is Fx. But same thing. When I sum the forces... they should be equal to 0, so we're going to have S1 minus S3 minus Fx. It's still 0, so you get the same thing. So it was just, that was pretty cool, and it was hard for me to see that you could take a system of vectors, and then you can multiply and divide. I don't know how you're going to, you could divide by a scalar, I get that, but you can't divide by a cross product. You can only do the cross product, which is a form of multiplying. So you could have a system of equations where I have S1 plus S2 plus S3. I'm probably going to say something wrong, but no, that's good. And then I'm going to multiply both sides. And then I'm going to have this Q cross all of these, and then Q cross all of Q cross that. So if I cross Q with both sides, did I change the problem? And alright, so I don't think so, but I'm not going to try to explain that. Because the solution to this problem, and sorry it's just so busy, but we're going to be done hopefully fairly soon. So you have your system of equations, S1, S2, S3, and then F, and those are going to be equal to 0. But then here was the solution. If you took the cross product, if you had S1 cross S2, what you're going to get there is a perpendicular vector. That's perpendicular to both S1 and S2. So if I have two vectors, S1 and S2, then what I'm going to do is I can, by crossing those together, I get a perpendicular, so this pen is the perpendicular vector. So that's the definition of crossing. It's like, hey, when I open a door, I put a force here. It has a distance to the hinges, and if it's at a 90-degree angle, hell yeah. Whatever force I put in, 100, and then the distance maybe 5, hey, I get a torque of 500. But if this distance, this angle isn't perpendicular, that's what the cross product hashes out. If this distance is like this way, kind of towards the hinges, I only get a proportion. And if it's a 45-degree angle, I'm only going to get 70% of this. So I'm going to get 70% in this direction. That's actually useful. 70 times 5, I would be at 350. So that's how that would work. But what this does is it generates. So if this is my force, so if I say, and actually I would do it this way. From the hinges, so the door, from the hinges, I'm going to have a vector. And I don't know, sometimes I've done this where I do a double arrow. I've never seen anyone do a double arrow, but it indicates, I like it because it's not a, it's not just like it's not like a, it's not a force, it's a torque. And that torque is going to act on those hinges. And if you have some way to designate that a torque allows things to spin around that axis, then maybe a double arrow is the way to go. I don't know if I've ever, I swear I saw this once done like this, but now this is going to be the resultant of this distance crossed with, so now I'm going to do a force this way, opening the door this way. Here's my R, here's my F, and we have R cross F. And then the right-hand rule says we're going to have a positive moment, which just means we have a counterclockwise direction of spin. And that's going, yeah, so R cross F is, if this is 90 degrees, R cross F is just going to be R times F. And that's going to be the magnitude, but it's going to have a direction in, let's say this is the K-hat direction. And we have X, no, this would be your X, Y, X, Y, I hat. So this is how you do your cardinal directions. I hat cross J hat should be K hat. Make sure to do, yeah, anytime you're setting up a coordinate system, do your X and Y, but then, or do your coordinate system, just make sure, put your fingers in X, rotate them into Y, and your thumb should be pointing in that K direction. Alright, so this problem was cool because you would cross S1 and S2, and you're just getting this extra vector. Cool. And so then this vector is perpendicular to both S1 and S2. So back to this, hard to show. But if I have this vector now, and I dot this vector into both S1 and S2, a perpendicular vector, a dot product only says, hey, if I have a vector this way, and it's kind of shadowed over this direction, and like and let's say it's at a 60 degree. If it's at 60 degrees, only half of this length is going to shadow onto here. If it's a small angle, pretty much almost like 90, 95%, 100%. So if I'm totally in this direction, I get 100%. And so that's the dot product. I'm taking this magnitude and then multiplying it by the vector in this direction. If this is 100 and this is 100, hell yeah, I'm going to get 10. I'm going to get 10,000. Here I'm going to get 5 5,000, you know, a 60-degree angle. And here I'm going to basically pretty close to 10,000, you know what I mean? But if this is a unit vector, hell yeah, it's going to be the percentage of this in that direction. But if this vector is perpendicular, there is no shadow. So if I take this, so I just crossed S1 and S2, and I get a vector. And so if I have that, and then go back and then dot it with S1 and S2, that's going to generate 0. So it's just so fast. You can take S1 and cross it with S2. You get a vector, and if you took that vector and dotted it with S1 or S2, you know, separate, and both of them, you're just going to get 0. There is no shadow distance. The perpendicular, you know, if I draw a line that's perpendicular, what's that distance? Well, it's 0. Okay, so the home stretch is I have a system of equations, S1 plus S2 plus S3 plus F is equal to 0. And what I want to do, so separately, so on a side, I take S1 crossed S2, and this gives me a vector Q. You know what I mean? I wish I didn't use Q, but that's pretty decent. And then I can take, so that was totally of an aside. But I know that if I take this vector Q and then I dot it, so I can take Q and then dot it with this whole system, which is the same thing as Q dot S1 individually plus Q dot S2 individually, and so forth. Q dot S3 individually plus Q dot F individually. And what we said, we get a scalar, but each of these is going to be S1 in the direction of Q. And we just said since we crossed S1 and S2, Q dot S1 is going to be 0. Q dot S2 is going to be 0. Q dot S3 will be... hell yeah, and this is, we're almost bringing it home, because this is the hardest part for me to see. If I take, so finally we get Q dot S3, hell yeah, we're going to get, this isn't perpendicular, we are going to get a number, but this should just be a scalar, right? But we can still pump the brakes, and we can still say that Q is, and Q doesn't need to be a unit vector. If you want Q to be a unit vector, it'll probably make your head it'll make your head spin less. Because I can take S1 and S2 and get Q. Now Q could be 55, it could just be a big number or whatever. And then when I dot it through, I'm still multiplying this. So I think the more mentally sane way to do it, even though it'd probably be a little more tedious with the numbers, is turn this into a unit vector. So I know it's 55, and I know it's in an I hat, J hat, and K hat direction. And so maybe it's 40, 15, and 10. You know what I mean? Maybe it's 40I, 15J, 10K, and the magnitude of that's going to be 55, but I want the unit vector. So I'm going to come in here, and then I'm going to go 40 squared plus 15 squared plus 10 squared. Kind of like Pythagorean's theorem. I'm not going to go through it, but Pythagorean theorem works in three directions. If I have a, I guess I am. If this is x, y, x, y, and z, to get up to this point, the distance to that point is going to be x squared plus y squared plus z squared is equal to c squared. All right, booyah. And then you'd have to take, and to get c, you'd take x squared plus y squared plus c squared and the square root of that. And so if you do that, if you turn this q into a unit vector, then you're just dotting in percentages. So we can do this. Hey, 40 is going to be, hey, maybe that's 80%. So this is going to be 0.8i plus plus 0.12 j plus oh, and it's not even going to be that way, because these would still be, this would be like 0.9 plus 0.15 plus 0.1. These do not equal 1. That's the take-home point. It's like, hey, it's not this. Don't get confused with 2, 1, and square root 5, where 2 plus 1 does not equal the square root of 5. So when you see these unit vectors, it's this squared. So especially, you're going to get like 0.9 and then maybe 0.1, 0.1. Yeah, that's going to equal like 1.15, but still it's the square of these. Once you square them, then those will equal 1 magnitude. But this is the percent in that I direction, percent in the J direction, and the percent in the K direction. Okay, so yeah, so I like this video because it shows that a dot product is taught that you just get this scalar. But you don't have to just get that scalar. You know what I mean? You can, and maybe I'm missing something fundamental. But what you can do is you can say, so let's say we have that unit vector of Q, and then we're dotting it with S1 and S2. Those were cross products, so those just become 0. But now I'm taking this unit vector. I'm going to put a hat on it since I know that now. A unit vector, you just put instead of a vector sign, you put a hat on it, which is vector Q divided by the magnitude of vector Q. Cool. And then I'm going to dot it with S3. But so I'm going to have this 90%. So S3 is also going to have, you know, some sort of number. S3, we don't know S3. So S3 is going to be S3 of xi plus S3 of xj plus S3 of xk hat. And then we're going to dot it with this. Let's say this is my my unit vector of Q. And so when doing the dot products, you only multiply like with like. So I have like 90%, 0.9 in the I, so I'm going to have 0.9 S3 of x. Cool. And then I'm going to add it with, okay, 0.15 S3 of, and I'm sorry, this is y and this is S3z. So this is the x component, y component, and the z component of S3. Okay, so I have S3y, and then I'm going to add 0.1 S3z. So I still don't know these three components, but I do now know their magnitude. I know that hell no, I think I did something just a little bit wrong. Yeah. No. So this S3 of x is 0.9 times S3. You know what I mean? So I'm taking whatever S3. Hopefully S3 is maybe like 205. Cool. That's what I'm kind of shooting for. And so I know the S3 of x component, the component of S3 in this x direction. So kind of that shadow component. That is S3 of x. So yeah. So when I dot product, I'm going to get 0.9 S3. All right, hell no, wrong again. So yeah, it's good to be wrong because yeah, sorry for just scratching this out. But no. This vector S3 does have an x component, a y component, and a z component. And we just said that we're dotting Q with S3. And so we're taking Q. Yeah, Q is like 0.9, you know. And that's Q is just a unit vector. And what was Q? Q was after we crossed S1 and S2. So visually we can do this. Here's S1, here's S2. We're going to get a vector perpendicular to that. And it's going to be in that direction. Let's say it has a unit vector of 1. And now we can see S3. This has to either be directly that way or directly in line with S3 to be 100% effective. If it's at a perpendicular distance, then dotting this vector, which we're calling Q, with S3 will generate 0. But we do see that we're going to get a shadow component in that direction. That's going to be, if we do the full scalar, that's what we're going to get. But this S3 also, this S3 direction is has 3 orthogonal components. It is in the z direction, the negative x, and then the y direction, going that way. Oh, and I see where the unneeded confusion is. Turning this into a unit vector did not help at all. It didn't matter what Q was, because we were saying that, hey, we're multiplying both sides by Q using the dot product. So yeah, let's go back to that. So we crossed S1 and S2, and you get Q. And Q does have Q is going to have a QXI plus QYJ plus QZ K hat. So that's going to be Q as a vector. And then we're going to dot it with S3 and F. And S3 and F are both going to have like an FXI plus FYJ plus FZ K hat component. That's going to be vector F, and the same thing with S3. Now, okay, hell yeah. So this does go back to this original. Sorry, it's so scratched up. But originally, I was saying, hey, if I dot F in the unit vector of I, then I get this component of F in that direction. And then I can do the same thing with S1, S2, and S3. I see that S2 doesn't have a component in the X direction, and so that's where we had that graph like this. This is X, this is our origin, and we were noticing that we have a vector F, a vector S1, and then a vector S2, S3. And so we just kind of reduced that portion of the problem down to this. And I guess I should have also gone over that if we take this vector F and dot it with the other two directions, we're going to get something that's in this Y direction. Here's the origin, and the F component is going to be this way. Just visually, the S2, if it's in tension, is going to be that way, and maybe it's smaller. So we have F, S2, S1 is smaller. Oh, S1 is going to be in tension, S1, and then S3. So we're going to get something that looks like that from the origin. And then we get in a system of equations in that direction. If I take this F, or if I take F and S1, S2, and S3, and then dot product with the Z direction, cool. Then I'm going to have this Z direction. Here's my origin. I'm going to have F coming down. All these are going to be tensions in the downward direction, and S2 is going to be the smallest. S1 and S3 are going to be the same. S1 and S3. So that's the equation that I'm going to get. And what happens is you have to solve all three of these simultaneously. Alright, hell yeah. So I'm going to slow down just a little bit because we have to get back to this original equation. S1, S2, S3 plus F is equal to 0. We dotted through this Q, but now, yeah, so now I kind of see it. If I dot Q with S1 and S2 individually, yeah, so this, this is cool because we don't do enough with vectors in America college at all. But what I know about the dot product and multiplication, it's, what is it, associative? Or is that commutative? Where this is going to be the same thing as Q dotted with S1 plus Q dotted with S2 plus Q dotted with S3 plus Q dotted with F is equal to 0. And it's still 0 dotted with Q, but that should be obvious. Okay, so now I know that the cross product that I took was S1 cross S2. So if I crossed S1 and S2, that's where I get this vector Q. And so when I dot it into S1 and S2, these are both 0. Okay, so now I'm just left with Q cross dotted S1 and plus Q dotted with F. But still, even here, this also is associative or commutative, where this is also QX just the way the dot product works. Like if I have this, I'm going to have the qx component in the I hat plus qy component j hat plus qz component k hat, and I'm going to dot it with s3x I hat plus s3 y j hat plus s3 z k hat. And when I do the definition of dot product is multiplying like terms. So the first thing I do is multiply qx and then s3x, and then I'm going to add it to qy s3y, and then add it to qz s3z. And I think a lot of stuff gets lost because it's just really repetitive and very tedious to to write all these subscripts. All right, cool. But I still did it in 3 separate steps, and each of these steps represent, like this types of scenario. So yeah, let's see if, and this dot product, this I hat is still a vector. So this is still the same. Yeah, I've never done this before, but yeah, this is the same thing as saying Q. This is the magnitude, but Qx I hat is the unit vector dotted with S3 x I hat. So this, and now that I'm dotting this, I get 100%. I dot I gives me 100% multiplication. Cool. And so that's going to be also, and then it's so it's plus qyj dotted with s3yj, and then qzk dotted with s3zk. So now I'm really liking this video because there's so much about learning that it's just like, hey, I don't mind telling you where I'm like not at and like where I'm trying to get. Because even in this video, like I've never done that before. Like use the associative or commutative or whatever properties, and then because just in the problem solution that the student gave, you just go from one step to the other like you know what's going on, but it's just like I have no idea. That's why I made this video, just to even get there. Because when all right, hell yeah, running out of juice here, but we got it. And then the same thing is going to happen with Q. You're going to get QXI dotted with FXI plus QYI dotted with FYJ. Sorry, QYJ hat. Did I get these all right? Yeah. FYJ hat plus QZK hat dotted with FZK hat. See, it just gets tedious. But then this gives you this. This now gives you, like this is its own equation. Just like I said, hey, we were doing the x direction, and then we were doing the y direction, and then the z direction. So this is my equation. This is my origin, and I'm going to have, I'm going to have q x s 3x this way, and then that's going to equal to qx fx that direction. And they're both multiplied, they're both scaled up by qx, and so that's where turning this into a unit vector didn't make, because if that was 0.9, you still have to scale it. You still have to factor it out. But yeah, this will just give you fx is equal to s3 of x, or more importantly, you know what fx is in this problem, so you have s3 of x is equal to fx. So doing the dot product gets you that last solution. And then the student in the video uses the matrix, and I need to use the matrix more. But you have so you have a matrix for Q. It's your QX, QY, QZ, and that's where people who use the matrix don't go over the fundamentals all the time. So you have no idea which like which is which. But then you're dotting this with the S3, which is S3X, S3Y, and S3Z. Which, you know, in the problem, you don't do it like that. You just say, hey, well, I already know the numbers of these. Let's say it's 1, 2, 3, so we got that. And then this is S3 dotted with the unit vector. Because going back to the actual geometry, the geometry shows you the percentages in, it looks like there's going to be a lot in the Z direction, 90% in the Z, and then just kind of 1 and 15% in the X and in the Y directions. So then the problem looked like this, where it was S3, you know what I mean? So like 0.9, or so like 0.1, 0.15, 0.9, something like that. And then this was going to equal, or let's say your F is just on the other side. I don't know why I'm doing that right now, but now you have your F's on the other side, so you have Fx, Fy, Fz. Now we're gonna dot that with that Q vector, Qx, Qy, Qz. F also, same thing, I don't know why I did it, but yeah, F also has dimensions on it, so we know that F is also just F, and then the unit vector in the F, and it looks like this is less in the down direction, more in the X, more in the Y, so maybe it's like 0.2, 0.8, 0.7, you know, something like that. And then so this is how dotting through that vector Q, which eliminated, because dotting with the other two that were crossed in, those go away, and then you were left with this. And I guess now I understand where I was confused, because you took Q and then dotted it with S3. Like, why do you get this little system of equations? Why don't you just get a scalar? And I think I need to do one more step. You do get a scalar. This is your scalar, but you just don't know S3 at all. So that's one way to look at it. Same thing here. This is your scalar for this dot product between F and Q, but you just don't know what F is. But yeah, again, it should be said that we don't know what F is, but we know the percentage is in the Fx direction. So that was due to geometry. We know the components in those X, Y, and Z directions. All right, sweet. So now we're gonna kind of do the home stretch, because and I think I'm kind of satisfied. The fact that we took a dot product of two vectors, each having three components, and we can use whatever the property associative commutative to separate those. This is still going to be a scalar, but we know that we have that situation where we have the I components over here, plus this was going to be that vector Q dotted with S, and then we have over here vector Q dotted with F. And so this is all just plus equal to 0. And so we're going to have this I component. Even though all this is just going to equal a number, it still represents what's happening in the I direction. And so I thought that was kind of cool, because I get confused with scalars, because it should just pop out a number, but while you're doing a scalar, it's representing what you're doing in the X, what you're doing in the Y direction, what you're doing in the Z direction. And so it seems like there should be another easier way to to show that without just saying a dot product is just generating a scalar. But you have this kind of in-between step that you can take advantage of. And maybe it's not that worth taking advantage of, because I just showed that, kind of in the problem statement that I was given, the student, just represented it in this way, where you had, and let's get numbers on these things. So you were taking Q dotted with S3 plus Q dotted with F equals 0. And we know the direction of, the direction of S3, because we can say that this is, we just know Q. So we know what that is. I'm just going to throw numbers 1, 2, 3 on that. And then we know this is dotted with S3, the component, the magnitude of S3, and then their directions. So, you know what I mean. You just have fractions of a whole. 0.3, 0.4, 0.5. Just keep it simple. And then over here, we're going to have same thing. Q, 1, 2, 3. Whoops, 1, 2, 3. And then we're going to have dotted with F, and then just the component. So we're going to have 0.5, 0.6, 0.7, let's say. And those are just the percentages in the direction where F is. Cool, is equal to 0. Now, this is going to give you, okay, so now I can see it from a visual perspective. This is just going to give you one big scalar. But then, the student followed this through, and the next thing to do is just S3, and then they just did this. They got 0.3, 0.8, 1.5. And it was just multiplying these numbers, and then you get plus, and then we get F, and then we get 0.5, 1.2, and then 2.1. So that's just multiplying 1 by 0.5, 2 by 6, and then 3 by that. And so that fascinated me. And now I see, like, it was fascinating to me, but now I can see that it's kind of unnecessary. But maybe it is necessary. I don't think so now that I see it, because when Oh, hell yeah. No, I see it. This really simplifies it. Because, now I have to go back, because this would say, just like we were saying, this problem has an x components, y components, and z components, and their dot products, their shadows. And then these have to be balanced, these have to be balanced, and these have to be balanced. Well, what I didn't really realize was the solution is that, hell yeah, this is going to say your x component of S3 is equal to your f component. You know what I mean? So the way this is done, and the reason that we have this new equation that says S is equal to F is because I think the dot product rotates the problem. Where, yeah, that's funny. It puts, yeah, so that also shows you, like, what the cross product does is, like, rotating to, let's say S1 was just down in these directions, but then S3 was just in that direction, where these components didn't have any component in that direction, and then you have this force, and this force has some sort of component in the x direction. Well, cool. The component of f of x has to equal S3 or whatever, the one that we're trying to solve. And so that's what we're doing. But we're still in the Cartesian coordinates, so we have rotated it in a specific way where we're still oh yeah. So in that form, what I just said, like put S1 and S2 just in this plane where they have no x component, and we put S3 with the total x component in that direction. And the only thing that can balance this force is, the component of the force in the x direction is S3 in the x direction. So if we were ended with that, that would be S3 maybe it's 0.3, but this would be 0, 0 plus f, and then you could have whatever. It wouldn't matter here for f, because when we add these, you know what I mean, your components, this is a system of equation. You have your x direction, your y direction, and your z direction, and this would just say 0.3 s3 is equal to 0.5 f, and then you could see that s3 is equal to 5/3 f. So that would be the solution that you would get. Now the way that they have it, the solution where you get something like this at the end, well, now all three of these have to be equal. Just because we did a cross product, we took this whole system, we dotted it with a direction that was perpendicular to S1 and S2, which was the same thing. And yeah, that's fascinating. It's like, sorry, I should have more sheets of paper. Which is the same, then this is a good visual. You could take this problem and just take an overhead view of it, get rid of the z component altogether, and just take an overhead picture, and then this f has no z component, and it's still, so now f is just in this xy. So its magnitude changes for sure, and then the magnitudes of S1 and S2 globally change, but their relationships don't. You know what I mean? The proportion of S1 to S2 to S3 is going to be the same whether you have this or you do an overhead picture, because you're projecting down on it. And so that's what the dot product does. The dot product takes this f, and if I dot it into this direction I, it's the shadow of f into, yes, the fx component. And the same thing, that would be the same thing as like, hey, you could take an overhead picture of this, and you're basically dot prodding it down, and I don't know what that would be called. Would that be, you would basically equally dot prodded it down in the x and y direction. That's what you would be doing. You're getting rid of the z direction. So you're taking all these vectors, dotting it into the x, and then taking them and dotting them into the y. And so you're getting the shadow of all these vectors on there. But like I said, the problem definitely changes. You're not going to get the same magnitude of S1, S2, and S3, but you're going to get the same proportions. So if you... sorry about that. No, I said that completely wrong. You get the same magnitudes of S1, S2, and S3. As long as you take the shadow component of f in this direction, and this is your new f. It has an x and y component. These are now, only have their x and y components. Yeah, the values will be the same. Because that's exactly what we're doing. We're trying to find the values of S1, S2, and S3, and instead of taking a bird's eye view down, what we're doing is okay, so now I can go back into words, because I'm glad I'm pausing. Because all of these vectors, S1, S2, and S3, they kind of have three different components. Well, except S2. S2 doesn't have a component in the x direction. So we can see that, oh cool, we have one tripod leg that has no component in the x. So that means, what that means is if it has no component in the x, and I take this vector and dot it into the direction of the x. So here's my x direction. There is no shadow. If I shine, if I go from the x-axis and go to every point on this vector, and these are perpendicular lines, so I would come down here, and this would be a perpendicular. If I went this direction, I wouldn't have a perpendicular line to the x. So yeah, and so that's going to be the shadow. Now the width of that shadow isn't There is no width of that shadow. So that's one scenario where the dot product of S2 in the x direction is 0. Okay, so taking the cross products of S1 and S2 generate this vector that's perpendicular to S1 and S2. So then if I say, so yeah, it's weird. For me, this is like juggling. I can see that this F has a component in the X, the Y, and then the Z. And so if I dot this F in this direction, I'm going to get some sort of percentage. It's at least something. But now let's say, let's just take this vector F. Let's say I come up with a new axis that's perpendicular. Then what if I take F and then dot it into this direction? What that says is how much of this F is in that direction? Well, none, because perpendicular is the definition of like, well actually no, and then that's the definition of the dot product. Having a dot product is the shadow of this in that direction. And it's just fascinating how S1 and S2, so here's S1 and S2, and you're taking a perpendicular vector. This is perpendicular to both of them. So now, what component of S1 and S2 is in this direction? Well, none. But then we can still say that F has a component in this direction. You know what I mean? And S3 has components in that direction. Or, and it's just one. Like, that's where the scalar comes in. If I have this S3 and this F, I'm taking this distance to wherever it hits horizontally, and then that's perpendicular, and then I'm as long as I take a string from this point of this vector to that axis, and as long as that's perpendicular, then I can take this string farther, shine a light on it, and this will shadow this vector, and it'll be that length. And so that's the component. So that's kind of the scalar perspective of dotting S3 with this new vector. You're going to get some sort of number on that. And that number has to equal the component of F in that direction as well. So if I have, and this plays because, hey, we have this down here, and then we're going to go a perpendicular distance. So yeah, you can just see that, hey, okay, so I see maybe this is this long, so this distance will, maybe those distances are actually equal. So even from that perspective, you can do this graphically as well, drawing your perpendicular lines as best as possible, and then seeing that those two are going to be equal. And if you're treating S1 as a unit vector in the direction of S1 times this magnitude S1, well then you are getting a scalar that's, you know what I mean? This is your length there, and if you do the same thing with F, if you take F as the magnitude F times the unit vector F, then you're also getting that that component there. You still have to multiply by F, so you're getting a number for that one, a number for that one, and those don't have to be equal, because that number is going to be multiplied by S1, and this number is going to be multiplied by F, so that's where you get, you know what I mean, you get S3 times that dot product in that direction of the perpendicular from S1 to that cross product direction, and this is 0.5. And there's no reason to worry about making sure that these are unit vectors or anything, because you're just going to, it's going to be a proportion anyway. And then you're going to end with a proportion. Alright, so I think this video is just more for me. But now I think I can explain it better the next few times around. So that was good. But yeah, it's just fascinating. And I have to go back to his solutions, because if that person got something where it was like this and it wasn't like this, where you would have so you have S3 this plus F this is these numbers can be different, but the proportions are going to be the same. So if I say S3 is equal to F, and then that proportion for all three of these are going to be the same. So that is the thing that I didn't really pick up on, but now I can go back and double check. And I think I'm done. Holy hell. This was a kind of a good one, kind of a bad one. It shows you the learning process. I've gotten more motivation for folks being like, yeah, do whatever the hell you want to do, and because it hasn't been done before. I don't know. You know what I mean? No one's just going to struggle and show you the struggle. The struggle's real. I mean, it leads to depression, and so and then there's this idea of doing things that are too easy and just keep doing that on repeat, and then being like, no, I want to learn more. So how do you stretch just a little bit and then struggle? Come up with wrong things, but then, you know, hopefully turn them over and then see how you can turn them into right things. I guess I'm showing my process. I'm sure there's better processes, but nah, it's a brutal, everything's brutal about learning math and physics. But hell yeah, but we do it. So thanks for joining me, and guess what? That's a video.